Hello, this is Mr. Ruby, and this is a reading of Newton's first law. Force. A soccer ball sits on the ground, motionless, until you kick it. Your science book sits on the table until you pick it up. If you hold your book above the ground, then let it go, gravity pulls it to the floor. In every one of these cases, the motion of the ball or the book was changed by something pushing or pulling on it. An object will speed up, slow down, or turn only if something is pushing or pulling on it. A force is a push or a pull. Examples of forces are shown in Figure 1. Think about throwing a ball. Your hand exerts a force on the ball, and the ball accelerates forward until it leaves your hand. After the ball leaves your hand, gravity, force on it, causes the path to curve downward. When the ball hits the ground exerts a force, stopping the ball. A force can be exerted in different ways. For instance, a paperclip can be moved by the force a magnet exerts. The pull of Earth's gravity, or the force you exert when you pick it up. These are all examples of forces acting on the paperclip. Figure 1 shows a force as a push or a pull. A golf club exerts a force by pushing on the golf ball. A magnet on the crane pulls the pieces of scrap metal upward. Combining forces. More than one force can act on an object at the same time. If you hold a paperclip near a magnet, you, the magnet, and gravity all exert forces on the paperclip. The combination of the forces acting on the object is the net force. When more than one force is acting on an object, the net force determines the motion of the object. In this example, the paperclip is not moving, so the net force is 0. How do forces combine to form a net force? If the forces are in the same direction, they add together to form the net force. If two forces are opposite directions, then the net force is the difference between the two forces, and it is in the direction of the larger force. Balanced and unbalanced forces. A force can act on an object without causing it to accelerate if other forces cancel the push or pull of the force. Look at Figure 2. If you and your friend push on a door with the same amount of force in opposite directions, the door opens but does not move, because you both exert forces of the same size in opposite directions on the door. The two forces cancel each other. Two or more forces exerted on an object are balanced forces if their effects cancel each other and they do not cause a change in the object's motion. If the forces on an object are balanced, the net force is 0. If the forces on the unbalanced, their efforts do not cancel each other. Anytime the force acting on objects are unbalanced, the net force is not 0, and the motion of the object changes. So let's look at Figure 2 here. When the forces of an object are balanced, no change in the motion occurs, but when the forces on an object are unbalanced, a change in the motion does occur. Two students pushing on the door, equal forces here, no change in the motion of the door. Unequal, unbalanced forces here, a change in the motion of the door. This isn't to mean that a net force of 0 means an object isn't moving. It just means that the object isn't changing or accelerating. Newton's first law of motion. If you stand on a skateboard and someone gives you a push, then you and your skateboard will start moving. You began to move when the force was applied. An object at rest, like you on the skateboard, remains at rest unless an unbalanced force acts on it and causes it to move. Because a force had to be applied to make you move when you and your skateboard were at rest, you might think The force has to be applied continually to keep an object moving. Surprisingly, this is not the case. An object can be moving even if the net force acting on it is zero. Newton's first law of motion describes how an object moves when no net force is acting on it. According to Newton's first law of motion, if there is no net force acting on an object, the object remains at rest. Or, if the object is already moving, it continues to move in a straight line with constant speed. Commonly known as an object in motion will stay in motion, an object at rest will stay in rest, unless acted on by an outside force. A bit of history in this section. The Italian scientist Galileo Galilei, who lived from 1564 to 1642, was one of the first to understand that a force does not need to be constantly applied to an object to keep it moving. Galileo's idea helped Isaac Newton to better understand the nature of motion. Newton was able to explain the motion of objects in 3 rules called Newton's laws of motion. In this section, we'll cover Newton's first law. Friction. Galileo realized the motion of an object does not change until an unbalanced force acts on it. Every day you see moving objects come to a stop. The force that brings nearly everything to a stop is friction, which is the force that acts to resist sliding between 2 touching surfaces, such as figure 3 shows. Friction is why you never see objects moving with constant velocity unless a net force is applied. Friction is the force that eventually brings your skateboard to a stop unless you keep pushing on it. Friction always acts on objects that are sliding or moving through air or water. Let's look at this figure 3. When 2 objects are in contact, they try to slide past each other. Friction keeps them from moving or slows them down. Without friction, the rock climber would slide down the rock. And friction slows down the sliding baseball player. Opposing sliding. Although several different forms of friction exist, they all have one thing in common. If 2 objects are in contact, frictional forces always try to prevent one object from sliding on the other object. If you rub your hand against the tabletop, you can feel the friction push against the motion of your hand. If you rub the other way, you can feel the direction of the friction change, so it again acting against your hand's motion. Friction always will slow an object down. Other ideas about motion. It took a long time for people to understand motion. One reason was that people did not understand the behavior of friction or understand that friction was a force. Because friction causes moving objects to stop, people thought the natural state of an object was to be at rest. For an object to be in motion, something had to be pushing or pulling it continuously. As soon as the force stopped, nature would bring the object to rest. Galileo understood that an object in constant motion is as natural as an object at rest. It was usually friction that made moving objects slow down and eventually come to a stop. To keep an object moving, a force had to be applied to overcome the effects of friction. If friction could be removed, an object in motion would continue to move in a straight line with constant speed. Figure 4 shows motion where there's almost no friction. Figure 4. In an air hockey game, the puck floats on a layer of air so that friction is almost eliminated. As a result, the puck moves in a straight line with nearly constant speed after it's been hit. How would the puck move if there was no layer of air? Well, it would slow down on the tabletop, not sliding easily between the 2 players. Let's look at some types of friction now. The first, static friction. If you ever tried pushing something heavy, like a refrigerator, you might have discovered that nothing happens at first. Then, as you push harder and harder, the object suddenly will start to move. When you first start to push, friction between the heavy refrigerator and the floor opposes the force you are exerting, and the net force is zero. The type of friction that prevents an object from moving when a force is applied to it is called static friction. It keeps things in place. Static friction is caused by the attraction between the atoms on two surfaces that are in contact. This causes the surfaces to stick or weld together where they are in contact. Usually, the surface gets rougher, the object gets heavier, the force of static friction will be larger. To move the object, you must have exerted a force large enough to break the bonds holding the two surfaces together. Our next look is sliding friction. While static friction keeps an object at rest, sliding friction slows down an object that slides. If you push an object across the room, you notice the sliding friction between the bottom of the object and the floor. You have to keep pushing to overcome the force of sliding friction. Sliding friction is due to the microscopic roughness of two surfaces as shown in Figure 5. A force must be applied to move rough areas off one surface past rough areas of the other. The brake pad in a car uses sliding friction against the wheels to slow down the car. Bicycle brakes, shown in Figure 6a, work the same way. Reading check. What's the difference between static friction and sliding friction? You're right. Static friction keeps things in place. Sliding friction slows things down that are in motion. Figure 5 shows a cafeteria. Microscopic roughness, even on the surfaces seem smooth, such as the tray and metal shelf, cause sliding friction. What do you think lubricant does? It reduces the sliding friction. And now, finally, rolling friction. Another type of friction, rolling friction, is needed to make a wheel or a tire turn. Rolling friction occurs between the ground and the part of the tire touching the ground, as shown in Figure 6b. Rolling friction keeps the tire from slipping on the ground. If the bicycle tires are rolling forward, rolling friction exerts a force on the tires that pushes the bicycle forward. It's usually easier to pull a load on a wagon or cart that has wheels rather than drag the load along the ground. This is because rolling friction between the wheels and the ground is less than the sliding friction between the load and the ground. One last look here at Figure 6 of bicycles, sliding friction and rolling friction. A. Sliding friction is used to stop the bicycle tire. Friction between the brake pad and the wheels bring the wheel to a stop. B. Rolling friction with the ground pushes the bottom of the bicycle tire so it rolls forward. And that has been the reading of Newton's first law. Let's go over some highlights. A force is a push or a pull. This you should remember. Combining forces. A net force is all the forces together, whether it's both pushing at the same or one pushing stronger than the other. Balanced forces, there'll be no change in acceleration, no speeding up, slowing down, or change direction. Unbalanced forces will cause a change in acceleration, the speeding up, the slowing down, or the change in direction. Newton's first law. An object at rest will stay at rest. An object in motion will stay in motion unless acted on by an outside force. Friction. This is most likely the outside force that we encounter every day. This is why things don't keep on moving and rolling once we start them in that motion. Types of friction. Static, which holds things in place. Sliding, which slows things down. And rolling friction, which gives you the ability to push off from the ground or other places so things such as bicycles and cars can move. And finally, older ideas about motion. And this is intuitive to some, that you look at something, you think it should stay at rest always, and that was the idea, until Galileo came along. Then Isaac Newton confirmed that an object in motion will stay in motion, an object at rest will stay at rest, unless acted on by an outside force. This has been Mr. Ruby, and once again, this was Newton's first law. Thank you for tuning in. I hope you've enjoyed music by Handel, who was alive during Newton's time. So long, farewell, and please like and subscribe.